Have you ever looked up at the night sky and felt a profound sense of loneliness, a feeling that in the vast, silent expanse of the cosmos, we are utterly and completely alone? It's a thought that has haunted humanity for millennia, a cosmic whisper that shapes our philosophies, our religions, and our science. But what if that silence is about to be broken? What if a visitor is knocking at our door, not with a sound, but with a trajectory, a path so precise, so improbable, that it screams of intelligence? We are standing on the precipice of a revelation that could redefine our place in the universe, and it all hinges on a single mysterious object named Atlas, hurtling towards us from the interstellar darkness. This isn't just a story about a rock in space. This is a story about a choice. The choice to dismiss the anomalous, or the courage to face the possibility that we are about to meet the neighbors. And the date you need to circle on your calendar, the day our reality might just shatter, is October 29th. The question is, are you ready for what comes next? The story of our cosmic solitude began to unravel not with a bang, but with a faint speck of light moving against the backdrop of distant, unblinking stars. In the grand, silent theater of space, where comets and asteroids are the routine players, a new actor has taken center stage. We call it Atlas. Officially designated C2023A3, Tsuchinshan-ATLAS, it is only the third known object to have entered our solar system from the vast, uncharted territory of interstellar space. The first was Oumuamua, a bizarre, cigar-shaped anomaly that tumbled past us in 2017, leaving a trail of unanswered questions. The second was Borisov, a more conventional, albeit still extraordinary, interstellar comet. But Atlas is different. It is distinguished not merely by its foreign origin, but by its two most staggering characteristics: its immense size and its incredible velocity. It is a bullet fired from the depths of the galaxy, and it is headed directly for the heart of our solar system. At the center of this unfolding cosmic drama stands a figure no stranger to controversy: Harvard astrophysicist Avi Loeb, a man whose mind operates on the razor's edge between rigorous scientific inquiry and daring imaginative speculation. For Loeb, the arrival of Atlas is not just another astronomical event to be catalogued and filed away. He sees a pattern, a series of coincidences so profound they challenge the very notion of chance. The central mystery, the axis around which this entire enigma revolves, is a specific date: October 29th. On this day, Atlas will perform a celestial vanishing act. It will disappear behind the sun, a moment astronomers call perihelion, its closest approach to our star. From our vantage point on Earth, it will be completely hidden from view, masked by the sun's blinding glare. Mainstream astronomy sees this as a simple, predictable orbital mechanic. A celestial body, captured by the sun's gravity, will swing around it like a stone in a sling and be flung back out into the void. But Avi Loeb posits a far more unsettling and frankly terrifying possibility. He argues this is not a coincidence. It is an opportunity, a perfectly timed, strategically brilliant moment for Atlas to perform a maneuver, to fire an engine or deploy a solar sail, using the sun's immense gravity as a slingshot not to escape, but to slow down, to brake, and to enter a permanent, stable orbit within our solar system. It is, in his view, the perfect way for an intelligent probe to arrive undetected, using our own star as a celestial smokescreen. The foundation of Loeb's audacious argument is built upon a cascade of statistical improbabilities, a series of cosmic dice rolls that all seem to be coming up sevens. The first and most glaring of these is the sheer size of Atlas. When it was first detected, astronomers calculated its brightness, or albedo. Based on how much light it was reflecting, initial estimates placed its diameter at a colossal 20 kilometers. To put that into perspective, that is larger than the island of Manhattan. It is twice the size of the asteroid that wiped out the dinosaurs. An object this massive is a true cosmic monster. Now here's where the statistics become unnerving. Based on our current understanding of the galaxy and the distribution of objects within it, we have models that predict how often we should encounter interstellar visitors of a certain size. These models are built on a simple, logical principle. For every giant mountain, there should be millions of tiny pebbles. The universe, like a quarry, should be overwhelmingly populated by small rocks, dust, and ice. Large, planetoid-sized objects should be exceptionally rare. According to the established models, we should only expect to find an object the size of Atlas, a 20-kilometer behemoth once every 10,000 years of searching. And yet, here we are. We have only been systematically scanning the skies for these interstellar interlopers for a little over a decade. In that short span of time, we've found 3. The fact that one of them is a 1 in 10,000 year discovery is not just lucky. It is a statistical anomaly of the highest order. It defies the expected distribution of cosmic objects. Loeb puts it in stark, quantifiable terms. Before we ever spotted something as gargantuan as Atlas, we should have first discovered and catalogued at least 100,000 smaller, Oumuamua-sized objects. We haven't. We've found one. The numbers simply don't add up. It's like going to a beach for the first time and, instead of finding sand, finding that the entire shore is made of perfectly polished 10-carat diamonds. You wouldn't just call it a lucky day. You would immediately suspect that this beach is not a natural formation. This initial calculation of size, this first profound improbability, is the opening act of a much larger, more complex mystery. It is the first clue that suggests Atlas might be more than just a random piece of galactic debris. It forces us to confront a deeply unsettling question. Are we simply witnessing a series of incredible cosmic coincidences, a statistical fluke that will be talked about for centuries? Or are we observing the deliberate, calculated arrival of something engineered, something that chose its size and its timing with a purpose we are only just beginning to grasp? The vanishing act on October 29th is no longer just a predictable celestial event. It is a deadline. It is the moment when we might find out if we are alone, or if a new and perhaps permanent neighbor is moving into our cosmic backyard. The silence of space is becoming deafening, and every telescope on Earth is now pointed at this interstellar messenger, waiting for it to reveal its true nature. The enigma of Atlas is a moving target, a mystery that deepens with every new piece of data we collect. Just as the scientific community was grappling with the sheer statistical unlikelihood of a 20-kilometer interstellar visitor, the Hubble Space Telescope, our venerable eye in the sky, provided a new, more refined look. The updated observations brought a sigh of relief to many. The data revised Atlas's diameter down from the city-sized 20 kilometers to a more manageable, though still immense, 5.6 kilometers. This new figure, while still making Atlas a giant among comets, seemed to soften the sharp edge of the statistical anomaly. It was still a remarkably large object to find so soon, but perhaps not a 1 in 10,000 year miracle. For a moment it seemed as though Atlas might just be a very large, very unusual comet after all. But this sense of normalcy was short-lived, because a brand-new analysis, led by Loeb and his team, introduced a far more profound and perplexing complication. This new puzzle wasn't about size, but about mass. It emerged from measuring Atlas's trajectory with almost unbelievable precision. In astronomy, nothing moves in a perfectly straight line or a perfect orbit. Objects are constantly pushed and pulled by forces other than gravity. For a comet, the most significant of these forces is something called non-gravitational acceleration. As a comet gets closer to the Sun, its icy surface heats up and turns directly into gas, a process called sublimation. This outgassing acts like a series of tiny, unpredictable rocket thrusters, spewing jets of gas and dust into space. This gentle, persistent push is enough to subtly alter the comet's path, causing it to deviate slightly from the perfect orbit predicted by gravity alone. We see this effect in almost every comet we observe. The James Webb Space Telescope, with its unparalleled infrared sensitivity, was pointed at Atlas to confirm this very process. And confirm it did. The Webb telescope detected a significant plume of gas streaming from Atlas's surface. It was able to quantify the output with remarkable accuracy. Atlas is actively spewing approximately 150 kilograms of gas, mostly carbon dioxide, into space every single second. That's the equivalent of jettisoning the weight of a large adult human every second of every day. This is a substantial amount of thrust. A normal comet of Atlas's 5.6 kilometer size, venting that much gas, should be visibly wobbling and veering off its gravitationally defined course. Its trajectory should be messy, buffeted by its own outgassing. But here is the heart of the new mystery. It isn't. When Loeb's team analyzed Atlas's trajectory, tracing its path across the solar system, they found that it shows almost no discernible non-gravitational acceleration. It is flying true. It is moving as if the 150 kOEs of thrust isn't there at all. It holds its course with a stability and precision that is utterly baffling. How can an object be actively firing thrusters and yet not be moved by them? The laws of physics provide only one possible explanation: inertia. The only way Atlas wouldn't be visibly nudged by this significant ongoing thrust is if it were incredibly, incomprehensibly massive. The team went to work on the calculations. They asked, what is the absolute minimum mass an object would need to have for a 150 kilojoules thrust to produce no observable deviation in its trajectory? The number they arrived at was staggering. The new minimum mass for Atlas is 33 billion tons. Let that number sink in. Not 33 million, but 33 billion tons. This finding did more than just introduce a new complication. It completely resurrected the original statistical anomaly and made it even more pronounced. A 5.6-kilometer object that weighs 33 billion tons is orders of magnitude denser than any typical comet, which are often described as dirty snowballs, porous, lightweight aggregates of ice and dust. This immense mass, packed into a relatively small volume, brings us right back to the original problem, but in a new form: finding an object this massive so early in our search is just as, if not more, statistically improbable than finding a 20-kilometer one. We are once again faced with a 1 in 10,000-year discovery. The universe, it seems, should not be making objects like this and sending them our way with such frequency. This profound discrepancy between Atlas's observed outgassing and its unperturbed trajectory forces us into uncomfortable territory, pushing the boundaries of conventional explanation. It is this tension that gives birth to a new, highly speculative, yet scientifically plausible possibility. Avi Loeb proposes a solution that elegantly solves the paradox. Atlas may not be a solid rock. Think about it this way: how can something be very large and yet not be as dense as a solid object of its size, while still possessing enormous mass? The answer is that it could be a hollow, engineered structure. Imagine a colossal, thin-shelled vessel, perhaps kilometers in diameter. The structure itself, the hull, would account for the immense 33 billion-ton mass. This would explain its inertia and its resistance to being pushed around by outgassing. The 150 kilojoules of gas the Webb telescope sees would not be the result of a sublimating cometary nucleus, but perhaps something more akin to venting, or the sublimation of a thin layer of cosmic frost accumulated on its surface over its long journey through interstellar space. This hypothesis, as extraordinary as it sounds, is a direct consequence of the data. It is not a flight of fancy, but a potential solution to a set of observations that do not fit our natural models. The idea of a hollow, engineered object neatly explains how Atlas can be so massive without being as dense as a solid natural body. It reconciles the powerful outgassing with the eerily precise trajectory. It transforms ATLAS from a geological anomaly into a potential technological artifact. The problem of its size and mass is no longer just a question of cosmic statistics, but a question of design and purpose. We are no longer just looking at a big rock. We are potentially looking at a ship. A very old, very large, and very, very heavy ship. If the sheer size and mass of ATLAS present a compelling statistical mystery, its trajectory transforms that mystery into a powerful argument for intent. The path an object takes through the cosmos is its autobiography, telling the story of every gravitational nudge and pull it has experienced over eons. For random interstellar visitors, these paths should be, by definition, random. They should slice through our solar system at arbitrary angles, heedless of the neat, orderly structure within. But ATLAS's path is anything but random. The argument for fine-tuning is built by layering a series of orbital coincidences, each one improbable on its own, but which, when combined, paint a picture of a trajectory that seems less like a cosmic accident and more like a carefully plotted course. The first and most fundamental of these coincidences is its alignment with the ecliptic plane. Our solar system is, for the most part, flat. The planets, from Mercury to Neptune, all orbit the Sun in a relatively thin disk, like marbles rolling on a dinner plate. This is the ecliptic plane. An object arriving from interstellar space, having been thrown out of its own star system by some chaotic gravitational event, should have no knowledge of or relationship to our solar system's specific orientation. It should arrive from a random direction, from high above the plane, from far below, or at any conceivable angle in between. The odds of an interstellar visitor happening to arrive on a path that is almost perfectly aligned with our flat planetary disk are slim. But the story of ATLAS's trajectory doesn't end there. It gets far more improbable. As it journeys through our solar system on this suspiciously flat path, its trajectory brings it into remarkably close proximity with not one, not two, but three different planets: Jupiter, Mars, and Venus. And it doesn't just fly by their general vicinity in space. Its timing is such that it encounters them at the precise moments when those planets are actually there. Consider the sheer emptiness of space. Even within our solar system, the planets are tiny specks in a vast, three-dimensional void. The chances of a random object's path intersecting the orbit of a single planet are low. The chances of it arriving at that intersection point at the exact same time as the planet are far lower still. ATLAS manages to do this for three separate planets. It's like planning a cross-country road trip, and not only passing through three specific small towns, but arriving in each town on the exact day of their annual street fair, all without ever looking at a map or a calendar. Loeb, ever the statistician, ran the numbers on this series of planetary flybys. He calculated the combined odds of these three specific encounters happening purely by chance during a single passage through the solar system. The most immediate and intriguing of these encounters is the upcoming Mars flyby on October 3rd. This event is highlighted as more than just a gravitational curiosity. It is a potential moment of action. From the perspective of an intelligent probe, a close flyby of a planet like Mars, a primary target for human exploration, and a world of immense scientific interest, is a golden opportunity. Loeb speculates that this could be the perfect moment for ATLAS to deploy a smaller secondary probe, something small, stealthy, and perhaps impossible for us to detect from our distant vantage point on Earth. It could be a maneuver to release a lander, an orbiter, or a reconnaissance drone to study the red planet up close, all while the parent craft continues on its primary trajectory towards the Sun. The Mars flyby is a testable hypothesis. While we may not be able to see a small probe being deployed, any change in ATLAS's own trajectory, however minute, after the flyby would be a smoking gun, irrefutable evidence of a deliberate action. This entire chain of improbable events, the ecliptic alignment, the three-planetary rendezvous culminates in the perfect timing of its October 29th perihelion. This is the grand finale of its inbound journey. The fact that it will be completely hidden from Earth's view at the precise moment of its maximum velocity and closest approach to the Sun is, in this context, the ultimate tactical advantage. It is the ideal cover for its most critical maneuver, breaking into a permanent orbit. It uses our own star as a shield, ensuring that its most revealing action, the one that would unambiguously prove its artificial nature, happens while we are all looking the other way. The trajectory of Atlas, when viewed through this lens, is no longer a passive arc shaped by gravity. It appears to be an active, intelligent, and finely tuned sequence of events, designed to maximize observational opportunities while minimizing detection. It is a journey with purpose. The question that hangs in the air, as heavy and as massive as Atlas itself, is, what is that purpose? And what happens after October 29th, when the vanishing act is over, and the visitor decides to stay? Beyond the compelling mathematics of its size, mass, and trajectory, the enigma of Atlas deepens when we turn our telescopes towards it and examine the direct visual and chemical evidence. What we see clashes directly with the established profile of a typical comet. Comets are famously defined by their tails. As these icy bodies approach the Sun, they heat up, and the sublimating gas and dust are pushed away by the solar wind and radiation pressure. This creates a spectacular tail that always, without exception, streams directly away from the Sun, regardless of the comet's direction of travel. It is the most fundamental and recognizable characteristic of a comet. However, early images of Atlas captured by the Hubble Space Telescope showed something profoundly strange, something that defied this basic principle. In those initial observations, Atlas displayed an unusual forward-facing glow. It was a coma, a cloud of gas and dust, but it was concentrated in front of the nucleus, in the direction of its travel. Avi Loeb, with his characteristic flair for evocative language, described it perfectly. It was as if Atlas had headlights instead of a tail. This is simply not something natural comets do. The forces of the Sun are absolute. The tail must point away. The presence of a forward-facing glow, however temporary, is a significant anomaly that suggests a different process at play. While a more conventional sunward-pointing tail did eventually form as Atlas drew closer to the Sun, the initial headlight phenomenon remains a puzzle. Loeb speculates that this could be evidence of something other than natural sublimation. Perhaps what we were seeing was not a tail at all, but surface debris being shed from a technological object. He offers a relatable analogy. Imagine frost on the windshield of a car. As the car moves and the defroster warms the glass, the frost doesn't neatly flow off the back. It sublimates and dissipates in complex, sometimes forward-moving eddies. Could the headlights of Atlas have been the result of a thin layer of interstellar frost, accumulated over millions of years, burning off the windshield of an artificial construct as it entered the warmer environment of our solar system? This interpretation transforms a visual anomaly into a potential clue about the object's very nature and long history. The mystery of Atlas's appearance deepened dramatically during a lunar eclipse. In a moment of serendipitous astronomical alignment, observers were treated to a stunning and unexpected sight. Atlas began to emit a vivid, almost emerald green glow. In cometary science, a green glow is not unheard of. It is typically the signature of diatomic carbon, C2, a simple molecule that fluoresces with a characteristic green light when excited by solar radiation. However, in the case of Atlas, this sudden appearance was deeply puzzling. The reason for the confusion lay in earlier spectroscopic analysis of the gas surrounding Atlas. Spectroscopes are instruments that break down light into its constituent colors, allowing astronomers to identify the chemical elements present in a celestial object, much like a prism separates white light into a rainbow. Those earlier readings had shown that Atlas's coma was surprisingly depleted of diatomic carbon. The very ingredient needed to produce the green colors seemed to be missing. So where did this brilliant green glow suddenly come from? This discrepancy between the earlier chemical analysis and the later visual observation is a significant contradiction that has yet to be explained by conventional cometary models. It suggests that our understanding of Atlas's chemical makeup is incomplete, or that the object is undergoing processes that are not typical for a natural comet. Perhaps the most compelling piece of chemical evidence comes from the James Webb Space Telescope, which has the power to analyze the composition of the gases venting from Atlas in unprecedented detail. The Webb telescope found an astonishingly high ratio of carbon dioxide, CO2, to water ice, H2O. The data indicates an 8.1 ratio, meaning there is 8 times more carbon dioxide than water ice sublimating from its surface. This is one of the highest CO2 to H2O ratios ever recorded for a comet. While not impossible for a natural object, this peculiar chemical signature is highly unusual. It also opens the door to a fascinating and speculative interpretation from an engineering perspective. If you were to design a large technological object for a long journey through the cold of interstellar space, and you wanted to protect it from the thermal stresses of entering a new star system, what would you coat it with? Carbon dioxide ice, also known as dry ice, has specific thermal properties that could make it an ideal ablative heat shield. It sublimates at a very low temperature, carrying heat away efficiently and protecting the structure underneath. The 8:1 ratio might not be a geological accident, but a deliberate engineered coating designed for thermal protection upon arrival. The chemical signature in this light is not a record of its natural formation, but a feature of its technological design. Each of these pieces of evidence, the headlights, the mysterious green glow, the extreme chemical ratio, can, in isolation, be potentially explained away as the behavior of a very unusual or atypical comet. However, when viewed together, they form a compelling pattern of anomaly. The visual and chemical data consistently deviates from our expectations, painting a portrait of an object that simply doesn't behave the way a chunk of natural rock and ice should. The evidence from afar suggests that Atlas is more than it appears, and that its secrets are written not just in its trajectory, but in the very light and matter it sheds as it cuts its path towards the sun. As the mountain of anomalous data surrounding Atlas grows, the central, unspoken question becomes impossible to ignore. What would it actually take to prove that this object is artificial? How do we move from compelling suspicion to scientific certainty? This is where the narrative shifts from the analysis of data to the methodology of discovery. Avi Loeb, deeply frustrated by the scientific community's lack of a clear framework for addressing such a profound question, introduces his own proposal: the Loeb scale. The Loeb scale is designed to be a clear, practical 0 to 10 rating system to classify the likelihood that an interstellar object is technological in origin. It is modeled after similar scales used to assess other risks and phenomena, like the Richter scale for earthquakes or the Torino scale for asteroid impact hazards. A score of 0 would be reserved for an object confirmed to be natural, like a typical asteroid or comet. A score of 10 would represent incontrovertible proof, say a high-resolution image of a metallic hull with right angles, or the reception of a structured radio signal. In this framework, an object like Oumuamua, with its strange shape and non-gravitational acceleration without a visible coma, might score a 3 or 4. Atlas, however, with its multiple independent lines of anomalous evidence, the statistical improbability of its mass, the fine-tuned trajectory, the forward-facing headlights, the unusual chemical signature, would, in Loeb's view, score significantly higher. He argues that any object that scores above a 5 on this proposed scale should trigger an immediate, coordinated, international scientific response. It should be treated not as a fringe curiosity, but as a top priority scientific target, commanding the full attention of our best observatories and our brightest minds. This proposal highlights a glaring and, to Loeb, dangerous omission in our global planning. We, as a species, are fundamentally unprepared for a first contact scenario. We have detailed internationally agreed-upon protocols for dealing with other global risks. The discovery of a planet-killer asteroid headed for Earth would instantly trigger a pre-planned set of actions involving NASA, the ESA, and other space agencies. We have global frameworks like the Paris Agreement to address the slow-motion crisis of climate change. We have pandemic preparedness plans, but for the event that could arguably have the single greatest impact on human history, the confirmation that we are not alone in the universe, we have nothing. There is no plan, no protocol, no designated organization to lead the response. We are, in essence, flying blind. Loeb laments this lack of preparation, seeing it as a failure of imagination on the part of the scientific and political establishment. The potential discovery of extraterrestrial technology is a planetary issue that demands a unified planetary response. Who would speak for Earth? Who would coordinate the scientific investigation? Who would handle the public announcement and manage the inevitable social, political, and existential fallout? The fact that we have no answers to these questions is, for Loeb, a profound dereliction of duty. The chapter then briefly but chillingly touches upon one of the reasons why such a protocol is so desperately needed: the dark forest hypothesis. Derived from the science fiction novel The Three-Body Problem by Liu Cixin, this hypothesis offers a terrifying solution to the Fermi paradox, the question of, if the universe is full of life, where is everybody? The dark forest theory posits that the universe is like a dark forest, filled with silent hunters. Every civilization is a potential threat. The safest course of action for any intelligent species is to remain silent and hidden, because to reveal your existence is to invite your own destruction by a more technologically advanced predator. In this scenario, any civilization that broadcasts its presence is naive and will be swiftly eliminated to remove a potential future competitor. This hypothesis underscores the serious and potentially existential implications if Atlas is indeed a technological probe. We cannot assume that its intentions are benign. The vast outgassing detected by the Webb telescope could be interpreted not as harmless venting, but as the exhaust from a powerful engine. The fine-tuned trajectory could be seen not as an observational tour, but as a targeting solution. The silence of Atlas, its lack of any obvious communication signals, is, in the context of the dark forest, not a sign of its inert nature, but a sign of its tactical intelligence. It is behaving exactly as a cautious, potentially hostile hunter would. This forces us to confront the central question of the chapter on a much deeper level. The question is not just, is it alien technology, but what do we do if it is? Our lack of preparation means we are facing this profound moment with a dangerous combination of ignorance and disorganization. The Loeb scale is more than just a classification tool. It is a plea for a systematic, rational approach to a mystery that has the potential to be either the greatest discovery in human history or the gravest threat we have ever faced. Returning to the hard, cold, and incredibly heavy numbers, this chapter focuses on the most stubborn and difficult-to-explain aspect of the Atlas enigma, its staggering 33 billion-ton minimum mass. This is not a number that can be easily dismissed as an observational error or a statistical fluke. It is a direct calculation based on its observed outgassing and its impeccably stable trajectory. To understand why this number is so problematic, we must view it through the lens of the galaxy's mass budget. The concept of a mass budget is a fundamental tool in astrophysics. It's a way of accounting for all the stuff in a given cosmic environment. Just as a household has a financial budget, a certain amount of income that can be spent on various things, the Milky Way galaxy has a mass budget. We can estimate the total number of stars, the amount of gas and dust in the interstellar medium, And from that, we can calculate how much rocky and icy material is available to form objects like comets and asteroids. Over billions of years, stars are born and die, some exploding as supernovae, seeding the galaxy with heavier elements. These elements coalesce into new star systems, and a certain percentage of this material gets ejected during the chaotic formation of planets. This ejected material, the cosmic debris, is what populates interstellar space. Astrophysicists have models that estimate this mass budget for interstellar objects. These models predict the distribution of object sizes we should expect to see. As we've discussed, these models are clear. Small objects should be incredibly common, while massive objects should be exceedingly rare. Based on the total amount of rocky and icy material available in our region of the galaxy to form such objects, finding something as massive as Atlas, with its 33 billion-ton weight, this early in our systematic search represents a profound statistical anomaly. It breaks the budget. It's like being an auditor for a massive corporation. You know their total revenue, their expenses, and their assets. Then, one day, a single unexplained transaction for $1 trillion appears on the books. It's a number so large it cannot be reconciled with the known financial structure of the company. It's an anomaly that forces you to question your fundamental understanding of the business. The mass of Atlas is that trillion-dollar transaction on the galactic balance sheet. Finding it so soon, as only the third interstellar visitor, is a discovery that challenges our fundamental understanding of how the galaxy manufactures and distributes its material. Loeb suggests that this deep tension, this irresolvable conflict between the observed mass and the predicted mass budget, can be resolved in one of three ways. The first possibility is that we are just phenomenally, absurdly lucky. This is the simplest explanation, and the one most favored by scientific conservatism. It posits that there is no deeper mystery. By sheer dumb luck, our solar system happened to be in the path of one of the rarest types of objects the galaxy can produce, and we happen to build telescopes powerful enough to see it at just the right time. In this view, Atlas is a winning lottery ticket on a cosmic scale. While possible, this explanation is intellectually unsatisfying for many scientists, as it relies on pure chance and discourages further inquiry into the anomaly. The second possibility is that our understanding of the interstellar mass budget is completely and utterly wrong. This is a more scientifically intriguing option. It suggests that the models we have built over decades of research are fundamentally flawed. Perhaps the galaxy is far more efficient at creating massive, rocky bodies than we ever imagined. Perhaps there are unknown mechanisms for concentrating heavy elements and forming gigantic planetesimals in interstellar space. If this is the case, then Atlas is a revolutionary discovery that will force us to rewrite our textbooks on galactic formation and evolution. It would be a profound and important discovery, but a natural one nonetheless. The third option is the most speculative, the most exciting, and the one that Loeb finds the most compelling. It is the possibility that Atlas does not belong to the natural mass budget at all. This option suggests that Atlas is not a natural, solid body, but a voluminous, hollow structure. An engineered object, a technological artifact, would not be subject to the same statistical constraints as a naturally formed one. Think of it this way. The natural mass budget predicts the number of solid mountains you'd expect to find in a certain area. Finding a mountain the size of Everest in the middle of a flat desert would be a profound geological anomaly. But finding a structure the size of Everest, like a great pyramid or a massive skyscraper, is not a geological question. It is an engineering one. Its existence isn't constrained by the geology of the desert, but by the technology and resources of the civilization that built it. If Atlas is a hollow shell, it resolves the tension completely. Its 33 billion-ton mass would come from its structure, its hull, not from being a solid chunk of rock. A civilization capable of interstellar travel would, by necessity, be a master of engineering on a colossal scale. Building a 5.6-kilometer-long, 33-billion-ton vessel might be a trivial feat for them. In this scenario, Atlas's mass is not a statistical improbability. It is a design choice. It is no longer a geological problem, but a technological one. This third option, while the most extraordinary, is the one that most elegantly resolves the profound contradiction at the heart of the numbers. It suggests that the mass budget doesn't add up for a simple reason. We are trying to audit the books of a natural system, when we should be looking at the blueprints of an artificial one. The entire narrative, with its cascading improbabilities and deepening anomalies, hurtles towards a single pivotal moment in space and time. October 29th. On this day, Atlas will reach perihelion, the point in its orbit where it is closest to the Sun, and moving at its absolute maximum speed. This moment is re-examined here in painstaking detail, not as a passive astronomical event, but as a moment of profound tactical and strategic significance. For an intelligent probe, this is the optimal moment to execute its most critical maneuver. The key to understanding why lies in a principle of orbital mechanics known as the Oberth effect. The Oberth effect states that a rocket engine is most efficient at changing a craft's energy when the craft is moving at its highest velocity. To put it simply, you get more bang for your buck from your fuel when you are already moving fast. It's like pushing someone on a swing. A small push applied at the very bottom of the arc, where the swing is moving fastest, has a much greater effect on its height than the same push applied at the top of the arc, where it is moving slowest. The Sun's gravity well is the ultimate swing set. As Atlas plunges towards the Sun, it gains incredible speed. At perihelion, it will be at its peak velocity. A probe that wanted to leave our solar system with maximum efficiency would fire its engines at this point to accelerate, using the Oberth effect to get a massive speed boost and fling itself out into deep space. But a probe that wanted to stay could perform what is known as a reverse Oberth maneuver. By firing its engines in the opposite direction of its travel, a braking thrust, at the moment of its highest velocity, it could shed a huge amount of orbital energy with a relatively small amount of thrust. This braking maneuver would be just enough to slow it down so that the Sun's gravity, which it has been fighting against, could finally win the tug-of-war. The Sun's gravity would capture it, converting its hyperbolic escape trajectory into a closed, elliptical orbit. It would be trapped. It would become a permanent new member of our solar system. The timing of this maneuver is, from a tactical perspective, perfect. On October 29th, the Earth will be on the exact opposite side of the Sun from Atlas. Our planet and the interstellar visitor will be separated by 186 million miles of plasma and blinding light. Our telescopes, our radar systems, everything will be completely unable to observe the event. Our own star provides the perfect natural cover for Atlas's most decisive action. We would have no knowledge of the maneuver as it happens. We would only discover it weeks later, in late November or early December, when Atlas is scheduled to re-emerge from behind the Sun's glare. This is the moment of truth. Astronomers have precise calculations for the trajectory Atlas should be on when it reappears. If it emerges on that predicted path, continuing on its way out of the solar system, then the mystery will remain, but the object will be just another fascinating, albeit unusual, natural anomaly. But if it re-emerges on a new trajectory, a slower, captured elliptical orbit, then the game changes entirely. A change in its trajectory after passing behind the Sun would be the smoking gun. It would be irrefutable proof of a controlled, powered maneuver, and therefore of artificial intelligence. This chilling possibility forces us to confront the most fundamental question of all: intent. Why would an alien probe want to stay? The potential motives are as vast and varied as the stars themselves, and they range from the wonderfully hopeful to the utterly terrifying. Perhaps the motive is peaceful observation. A probe could place itself in a stable orbit to study our burgeoning technological civilization, to learn about our biology, our culture, our science. It could be a cosmic anthropologist, a silent patient observer cataloging a new species for a galactic database. Alternatively, the motive could be resource gathering. Our solar system is rich in heavy metals, water, and other resources that might be valuable to a spacefaring civilization. Atlas could be a robotic prospector, the vanguard of a larger mining operation. Or we must consider the more sinister possibilities, those informed by the dark forest hypothesis. If Atlas is a hunter, its decision to stay could be a prelude to action. It might be moving into a strategic position to observe our capabilities or to deploy further assets. Its capture by the Sun wouldn't be the end of its mission, but the beginning of its primary objective. The silence from behind the Sun on October 29th could be the quiet before a storm we cannot yet imagine. The perihelion of Atlas is therefore the climax of this cosmic drama. It is a moment pregnant with possibility, a fulcrum upon which our entire understanding of the universe might pivot. We are left waiting, staring at an empty patch of sky behind the Sun, for an object to re-emerge. Will it follow the path of a comet, or the path of a conqueror? The answer lies hidden behind the Sun, waiting for its cue. The potential confirmation that Atlas is an artificial probe would instantly catapult humanity into a new and unnerving era. The philosophical and practical consequences of such a discovery are immense, forcing us to confront not only the nature of the visitor, but the nature of ourselves. Avi Loeb frames this stark new reality with a chillingly simple dichotomy. An interstellar visitor could come to save us or to destroy us. This chapter explores these two polar opposite scenarios and highlights humanity's complete and terrifying lack of preparation for either one. The first scenario is the hopeful saver scenario. This is the narrative that has fueled a century of optimistic science fiction. In this vision, the visitors are an enlightened, ancient civilization that has long ago solved the problems that currently plague humanity: war, disease, poverty, and environmental collapse. Their arrival would be the greatest gift in human history. They might share advanced knowledge, offering us clean, limitless energy, cures for our most devastating illnesses, or the secrets of faster-than-light travel. They could provide the wisdom and technological uplift needed to solve climate change and ensure the long-term survival of our species. Their presence would unify humanity, ending our petty squabbles in the face of a greater cosmic context. This is the dream of first contact, a benevolent, godlike intervention that elevates us to a new level of existence. At the other end of the spectrum lies the grim destroyer scenario, a possibility derived directly from the cold logic of the dark forest hypothesis. In this narrative, the universe is not a benign cradle of life, but a predatory arena. Any emerging technological civilization is a potential future threat. A more advanced, and therefore more cautious, civilization might operate on a simple, ruthless principle: eliminate any potential competition before it has a chance to become a threat to you. In this view, Atlas would not be a savior, but an exterminator. It might be a planet-killer weapon system, a berserker probe designed to sterilize any life-bearing world it encounters. Or it could be a scout, gathering data on our technological capabilities and societal vulnerabilities before a larger, more destructive force arrives. The destroyer scenario suggests that our first contact could very well be our last. The central, terrifying argument of this chapter is that humanity is completely unprepared for either of these outcomes. We have no unified protocols for communication if the visitors are peaceful, and we possess no credible means of defense if they are hostile. Imagine the saver scenario plays out, and Atlas begins to transmit a message after settling into its new orbit. Who on earth is authorized to respond? Do we send back the works of Shakespeare and Bach, or the mathematical constant pi? Does the President of the United States speak for humanity? The Secretary General of the United Nations? A committee of scientists? The first nation to respond might irrevocably shape the nature of our relationship with this alien intelligence, for good or for ill. A clumsy, misunderstood, or aggressive response could turn a peaceful encounter into a hostile one. Our lack of a pre-agreed-upon communication protocol is a recipe for chaos and potential disaster. Now imagine the destroyer scenario. What is our plan? What is our defense against a technology that can cross the vast distances between stars? Our most powerful weapons are designed for terrestrial warfare and would likely be utterly useless against a target with such advanced capabilities. We have no planetary defense system, no unified global military command that could coordinate a response. If Atlas were to deploy weapons or begin hostile actions, humanity would be a fractured, disorganized, and helpless target. Our species would face an existential threat with no plan, no leadership, and no hope. It is this profound state of unpreparedness that Loeb seeks to remedy. He strongly and desperately advocates for the creation of a new international organization, a kind of planetary council, tasked with creating these missing protocols. This would not be a world government, but a dedicated body of scientists, diplomats, ethicists, and military strategists responsible for thinking through the unthinkable. Their mandate would be to develop plans for every contingency: how to establish peaceful contact, how to verify intentions, how to de-escalate potential conflicts, and, in the worst-case scenario, how to coordinate a unified planetary defense. Loeb argues that the potential arrival of an interstellar visitor is not a national issue. It is a planetary issue. It is a moment that would affect every single human being on Earth, and it demands a unified planetary response. To continue to ignore this possibility, to fail to prepare for it, is the height of irresponsibility. Atlas is forcing our hand. It is a cosmic wake-up call. Whether it proves to be a savior, a destroyer, or just an interesting rock, its passage through our solar system has exposed a critical vulnerability in our ability to act as a unified species in the face of a truly global event. The question is whether we will heed the warning before it's too late. No extraordinary claim in science goes unchallenged, and Avi Loeb's hypothesis about Atlas is perhaps the most extraordinary claim of the 21st century. This chapter presents the strong, sober, and often dismissive counter-arguments from the mainstream scientific community. The backlash is not just a disagreement over data. It is a fundamental clash of scientific philosophy, professional credibility, and the very nature of the scientific method. At the forefront of the critique are prominent and respected figures like NASA's Tom Statler, a leading expert on asteroids and comets. For Statler and many like him, every single characteristic of Atlas that Loeb points to as anomalous can be explained by natural, albeit unusual, cometary behavior. They argue that Loeb is engaging in a form of anomaly hunting, cherry-picking data points that fit his narrative while ignoring more plausible, if less exciting, explanations. They assert, for example, that the claims of statistical improbability are a direct product of observational bias. We are, by definition, more likely to find large, bright objects than small, dim ones. Our survey telescopes are designed to spot things that move and reflect light. Therefore, it's not surprising that one of our first discoveries is a large one. Furthermore, they argue that we are more likely to find objects on trajectories like Atlas's, which bring them close to the sun and make them brighten considerably, simply because those are the easiest ones to see. Critics also point to the visual and chemical evidence and offer more conventional interpretations. The forward-facing headlights? Perhaps a result of a unique spin axis orientation, causing a specific vent to point forward temporarily. The mysterious green glow? Maybe a pocket of diatomic carbon ice was suddenly exposed and sublimated. The high CO2 ratio? While unusual, it's not unprecedented. There are known carbon-rich comets, and Atlas could simply be the most extreme example we've ever seen. For every anomaly Loeb presents as evidence of technology, The mainstream community offers a potential, if sometimes complex, natural explanation. Underlying this scientific debate is a deeper issue: Loeb's history and his public persona. Many in the scientific establishment view his claims about Atlas with deep skepticism because of his similar, highly publicized, and ultimately unproven claims about Oumuamua being an alien artifact. They see a pattern of sensationalism, a tendency to jump to the most extraordinary conclusion possible. Critics argue that this harms the credibility of the serious, methodical search for extraterrestrial intelligence, SETI. They fear that by constantly crying alien, Loeb is desensitizing the public and the scientific community, making it harder for real, credible evidence to be taken seriously when it eventually arrives. The debate is tinged with accusations that Loeb is more interested in writing best-selling books and attracting media attention than in engaging in the slow, cautious, and often tedious process of real science. This clash is ultimately a philosophical one, a collision between two different approaches to science. The scientific establishment operates on the conservative principle famously articulated by Carl Sagan: extraordinary claims require extraordinary evidence. From this perspective, the burden of proof is squarely on Loeb. The data for Atlas is intriguing, yes, but it is far from the extraordinary, unambiguous evidence needed to overturn the default assumption that it is a natural object. The null hypothesis must be presumed true until it is definitively falsified. Loeb, on the other hand, champions a more exploratory and, he would argue, open-minded view. He inverts the Sagan maxim, arguing that the cost of missing the discovery of a real alien probe is so astronomically high that it justifies investigating every anomaly with the utmost seriousness. He believes that the conservative, risk-averse nature of the scientific establishment creates a culture of intellectual suppression, where scientists are afraid to pursue unconventional ideas for fear of ridicule or loss of funding. He sees himself not as a sensationalist, but as a pioneer, willing to ask the questions that others are too afraid to ask. The debate over Atlas is therefore more than just a debate about a single object. It is a debate about the soul of science itself. Is science a conservative institution whose primary role is to protect the integrity of established knowledge from false claims? Or is it an exploratory enterprise whose duty is to push the boundaries of our understanding, even if it means risking being wrong? Atlas has become the focal point of this profound philosophical clash. The object itself will soon pass, but the debate it has ignited about how we practice science in the face of the unknown will resonate for years to come. The speculation, the debate, the statistical arguments, and the philosophical clashes will all soon be rendered moot by the arrival of new, hard data. The final chapter outlines the concrete upcoming timeline of events that will, one way or another, resolve the central mystery of Atlas. The narrative shifts from theory to a schedule of empirical tests, a series of dates with destiny that will provide the evidence needed to either support or demolish the extraordinary claims. The first key date on the calendar is the October 3rd Mars flyby. This is our first opportunity to get a truly close look at Atlas. As it passes the red planet, the high-resolution imaging science experiment, HiRISE camera aboard the Mars Reconnaissance Orbiter, will be turned to look not down at Mars, but out into space. HiRISE is one of the most powerful cameras ever sent into the solar system, capable of resolving details on the surface of Mars down to the size of a dinner table. While it won't be able to see a Manhattan-sized structure with that level of detail from millions of kilometers away, it will provide our best, sharpest, and most detailed view of Atlas's nucleus. This observation could reveal the object's shape, its rotation, and potentially even large-scale surface features. An image showing a clearly non-spherical, perhaps even angular shape would be a bombshell. Conversely, a clear image of a potato-shaped cratered rock would strongly support the natural comet hypothesis. Following the Mars encounter, All eyes will turn to the crucial date of October 29th, the perihelion. As Atlas vanishes behind the Sun, the world's scientists can do nothing but wait. The most powerful telescopes on Earth will be useless. This is the period of greatest uncertainty, the ultimate cliffhanger. During these few weeks, as Atlas makes its closest approach to the Sun and executes its potential braking maneuver, the fate of the hypothesis will be sealed in secret, hidden behind the glare of our star. The true climax of the story will arrive in late November and early December. This is when Atlas is predicted to re-emerge from behind the Sun. It will also be making its closest approach to Earth during this period, allowing for an unprecedented campaign of intensive observation from every major observatory on the planet, both on the ground and in space. Radio telescopes will listen for any potential signals. Radar systems will attempt to bounce signals off its surface to determine its precise shape, spin, and composition. Spectroscopes will analyze its outgassing in minute detail, and most importantly, astrometrists will measure its position with painstaking accuracy, plotting the first points of its new, outbound trajectory. This is the moment of truth where the two possible outcomes are laid bare. Outcome 1. Atlas re-emerges exactly where it is predicted to be, continuing on its hyperbolic escape trajectory out of the solar system. In this case, it will be remembered as a fascinating, record-breaking, but ultimately natural anomaly. It will become a legend in the annals of astronomy, the Great Comet of 2025, a celestial curiosity that sparked a wild and imaginative debate. Avi Loeb's theories will be largely dismissed as a case of over-enthusiastic speculation, and the scientific establishment will feel vindicated in its cautious skepticism. Outcome 1. Atlas re-emerges on a new path. Its trajectory has changed. It has slowed down and been captured by the Sun's gravity. If it stays, then everything changes. It would be a moment of seismic, species-altering importance. The debate would be over. The evidence would be irrefutable. It would be the single greatest discovery in the history of science, confirming that we are not alone in the universe, and that an intelligence from another star system is now in our cosmic backyard. The narrative, and indeed our human story, stands at this fork in the road. Atlas is more than just a scientific object of interest. It is a critical test case. Its passage will define how humanity approaches the future and increasingly frequent discoveries of interstellar visitors. It has forced us to confront our own biases, our lack of preparation, and the profound philosophical questions at the heart of our existence. What does a story like this, a story of a mysterious traveler from the stars, truly teach us? Beyond the orbital mechanics and the chemical signatures, the core lesson of the Atlas enigma is about the power and the necessity of curiosity. It's a lesson in how to look at the world, or in this case, the universe. We live our daily lives governed by patterns, routines, and expectations. We see a bird, we identify it as a robin. We see a cloud, we know it's a cumulus. Our brains are wired to categorize, to fit new information into pre-existing boxes. This is efficient, but it can also be a cage. Avi Loeb, whether he is ultimately proven right or wrong, is championing the idea of looking at the anomaly, the thing that doesn't fit in the box, and asking, why? Instead of immediately trying to force it into a box it doesn't belong in. In our own lives, how often do we dismiss an idea because it sounds strange? How often do we ignore a feeling or an observation because it doesn't fit with our preconceived notions of how things are supposed to be? The story of Atlas is an invitation to embrace intellectual courage, to be willing to entertain an extraordinary possibility without being afraid of being wrong. It's about maintaining a sense of wonder, about looking at the familiar sky and realizing that it could, at any moment, present us with something profoundly new. My advice, drawn from this cosmic drama, is simple. Cultivate your own inner scientist. Question your assumptions. When something doesn't add up in your life, in your relationships, in your career, in your understanding of the world. Don't ignore the discrepancy. Investigate it. Be brave enough to follow the data, even if it leads you to an uncomfortable or unconventional conclusion. The universe is infinitely more strange and wonderful than we can possibly imagine, and the greatest discoveries, both in the cosmos and within ourselves, are often hiding in the anomalies we are too quick to dismiss. So I leave you with this question to ponder. If you were to create your own Loeb scale for your own life, to measure the things you take for granted versus the things you question, what would you find? What interstellar visitor? What strange idea or unexpected opportunity have you dismissed because it didn't fit the neat trajectory you had planned? Thank you for joining me on this incredible journey to the edge of the unknown. I wish you all clear skies and curious minds. If you found this story as fascinating as I did, please consider subscribing to the channel and joining our community of explorers. Your support allows us to continue asking the big questions. Stay safe, be well, and never stop looking up.